All right, let's talk about the invisible glue that holds our entire world together. I'm talking about chemical bonds. Seriously, from the water you drink to the phone you're probably holding, it's all built by atoms linking up in these incredibly specific ways.
But here's a question to get us started. Why is it diamond, the hardest thing we know of, while wax is so soft you can squish it with your fingers? I mean, they're both made of atoms, right? So what gives? Well, the secret is in those tiny, powerful connections between the atoms, and that is exactly what we're going to break down. You see, it all boils down to one simple, universal drive that rules the atomic world. This constant quest for stability.
So what does stable even mean for an atom? Well, you've got to look at the VIPs of the periodic table, the noble gases. These guys are the rock stars of stability. Why? Because their outermost electron shell is completely full. They're content, they're unreactive, they're happy. And pretty much every other atom is a wannabe noble gas. They'll do whatever it takes to get that full outer shell.
And that whatever it takes, that's what a chemical bond is. At its heart, a chemical bond is just the force that holds atoms together after they've gamed the system by either giving away, stealing, or sharing their outermost electrons, which we call valence electrons, all to get that stable, noble gas configuration.
So this whole quest for stability really leads atoms down two main paths, which create the two main types of bonds we're going to talk about, giving versus sharing.
So here are the two big game plans. On one side, you have the ionic bond. This is a total transfer, a complete giveaway of an electron, and it usually happens between a metal and a nonmetal. Then on the other side, you've got the covalent bond, which is all about cooperative sharing between two nonmetal atoms. Okay, let's zoom in on that ionic bond. Once that electron transfer happens, you're not dealing with neutral atoms anymore. You have two charged particles, called ions. And the bond itself, it's this incredibly powerful electrostatic attraction. Think of it like an unbreakable magnetic force, pulling those positive and negative ions together.
And here's a perfect example. You take sodium, a metal, which has this one lonely electron in its outer shell that it's just dying to get rid of. Then you have fluorine, a nonmetal, which is just one electron short of a perfect full shell. It's a match made in heaven. Sodium donates its electron and becomes a positive ion. Fluorine happily accepts it, becoming a negative ion. And bam! Opposites attract and they lock together in a super strong ionic bond.
And this isn't just something that happens in a lab. These bonds are everywhere. That sodium fluoride we just made? Yeah, that's in your toothpaste. And of course, sodium chloride, that's just table salt. These powerful atomic giveaways are building the stuff we use every single day.
Okay, so if ionic bonding is like a transaction, a giving and taking, then covalent bonding is all about teamwork. This is where two nonmetal atoms both need electrons. So instead of one taking from the other, they come to an agreement to share electron pairs. This little shared arrangement creates a stable unit that we call a molecule. And not all sharing is created equal. Sometimes atoms share just one pair of electrons, which we call a single bond, like you see in chlorine gas. Sometimes they'll share two pairs for a stronger double bond, like in the oxygen we're breathing right now. And sometimes they go all in and share three pairs, forming an incredibly strong triple bond, like in nitrogen gas.
Which brings us back to our diamond. Its secret is that it's the ultimate example of covalent bonding. See, a diamond isn't just made of a bunch of separate molecules. It's one single giant molecule. Every single carbon atom is locked into 4 other carbons by these powerful covalent bonds, creating this massive interlocking 3D web. That's where its incredible hardness comes from. Now, ionic and covalent bonds are definitely the main players on the field, but chemistry has a few specialists up its sleeve too. So let's look at a couple of other bonds that have some really special talents. First up, metals. Metal atoms are, well, pretty generous with their outer electrons. They hold on to them so loosely that the electrons just kind of detach and form this free-flowing sea of electrons that swarms around all the now positive metal ions. So the metallic bond is just the attraction between that negative sea and the positive ions swimming in it.
And that whole sea of electrons idea, it perfectly explains why metals are so good at conducting electricity. When you apply a current, those free-moving electrons just start flowing, carrying the charge along for the ride. It's basically an electron superhighway.
Okay, next up, the hydrogen bond. Now this is really important. This isn't a bond inside a molecule, holding atoms together. No, this is a weaker but super important force of attraction between different molecules. It's like a special kind of stickiness that happens when hydrogen is part of a molecule with a very grabby atom like oxygen or nitrogen. And don't let that word weaker fool you. Hydrogen bonds, when they work together, are incredibly powerful. They're the reason your hair clumps together when it's wet. They're why water has such a high boiling point. They're even responsible for that little bit of friction that helps you turn the page of a book. They really are the unsung heroes of chemistry.
All right, let's bring this all home. We've seen the different ways atoms can connect. Now for the really cool part, how those tiny invisible decisions create the world we can actually see and touch.
So the big question is, how does an atom's choice to transfer or to share an electron end up determining whether a substance is a solid or a liquid, or if it dissolves in water or conducts electricity?
This is where it all clicks. Look at ionic compounds like salt. They have crazy high melting points because you have to pump in a ton of energy to break up that super strong attraction between all those ions. But for simple covalent compounds, you only need to overcome the weak forces between the molecules, so they melt really easily. This also explains why salt water conducts electricity. The ions are free to move and carry a charge, but sugar water, which is covalent, doesn't. The bond type dictates everything.
So, as we wrap things up here, it's just amazing to think that these simple rules aren't just abstract ideas. They are literally the blueprints for everything around us, from atoms to everything.
The next time you use a battery, or take an antacid, or wash your clothes, just remember you're harnessing the power of ionic compounds, materials built entirely on that simple principle of giving an electron away.
And what about the sharers? Well, the world of covalent compounds gives us the paint on our walls, the medicine in our cabinets, and the skincare products we use every day. The simple principle of sharing electrons is just as vital to our world.
In the end, it really all comes down to these tiny atomic handshakes, these fundamental forces that construct our entire reality. And it just leaves you with this one final thought. If we can truly master the art of making and breaking these bonds at will, what incredible new materials are just waiting for us to design?